Let's go ahead and take a look at quantifying the force of a current carrying wire. So on yesterday, what we did is we did a variety of discussions, demonstrations, and we went through this stuff here. I think we ended the day with the Carrington event. Talked about that as a potentially like earth-changing kind of thing if that happened in today's world because of the effects that it could have on our electrical power systems. Today what we want to do is we want to look at how we quantify force on a current carrying wire. You'll notice that none of this stuff is up here because this is the first time now that I've been able to get to the point in this class where I can get into Faraday's law. And I think it's an important thing. I've just never been able to get to it. So there's not the equations that we're going to be developing here would be going here, and I just don't have them up here. Okay, so people are going to be like, where's the equation? I don't have them. You'll see that the equations are fairly straightforward. The hard part is getting the direction down. Okay, so the demonstration I showed you guys yesterday was that we can have a wire be lifted or sort of vibrated by a magnetic field. I have a current flowing through this wire. That current is flowing, in this case, into the board. The magnetic field flows from the north to the south, and we notice that those are perpendicular to each other. The amount of force acting on that wire, and you guys saw evidence of that, we could lift that wire up or cause it to go down. That force is downward there. If I change the direction of the current, we still notice that the force is upward. What I want to do is I want to show you how we determine the direction of that current. So it is perpendicular to the direction of the current flow. So one of the things that affects it is the amount of current. It should make sense. If I have a greater rate of flow of charge, I'm going to be able to get a bigger force acting on it. It's perpendicular to the direction of the magnetic field. Now this might be the first time that we've seen the letter B. I don't know if you guys have seen it before. Yes? No? Okay, the symbol that we use for magnetism is, for a magnetic field, is a letter B. Now I'd like to know its units, and I see that Malcolm has his Chromebook up because he knows that I want to have him look up something, right? And then you're going to close that. So would you look up for me, please, the unit that we would use for magnetic field?
Tesla.
The Tesla. I wonder if Tesla is the same Tesla that was part of the Current Wars movie. You guys think maybe?
Yeah.
Probably. All right. So the unit that we use for magnetic field is measured in Tesla. So it's the new unit. It's the first time any of us have seen that. Okay, it's given by the right-hand rule. Now, I'm going to show you how to use the right hand to determine the direction of the force. It's really hard to do this on a video because the video does not pick me up showing that kind of stuff. I can't use the webcam. It doesn't work. I want you to take the fingers of your right hand. Those fingers of your right hand, you would put them in the direction of I. Now, if I do that for this first horseshoe magnet, the one on the left, the direction of I is into the board. So I would take my fingers of my right hand and I would point them into the board. Now, I have to take the fingers of my right hand and curl them in the direction of B. And I notice that B is pointed to the right. Would you guys agree? Is it to your right? It is. So what I have to do is I have to take my fingers of my right hand, point towards the board, like so, and I'm going to have it like this so that when I wrap my fingers in the direction of B, they curl towards the right. Notice my thumb is pointing down. My thumb is acting in the direction that the force would be exerted on the wire, so I'd push it downward. Now, if I change the direction of the current, you notice for the one in the middle, the current now is flowing out of the board. So what I'd have to do here is I'd have to take my fingers and point them towards you. I notice that it's pointed, it goes from north to south, so my fingers are curling that way, and I notice that now my thumb is pointed upward. So the direction of that force would be up. And what I demonstrated yesterday was I can use that alternating current to cause that speaker to go up and down. That has to do with the directional change of that force. Now, I would like you to see, I do not have the equation in front of you on purpose. I want to see if you guys can figure it out. What do you think the force depends on of these things up here? How would you write an equation? You're not going to look it up. What do you think it depends on? Do you think it would depend on I? Do you think it would depend on B? Does it seem like it might be a product of those two things or a division? What do you think? Would I multiply them? Would I divide them? Probably a product. Could I add or subtract them? Could it be equal to the sum of those things? Absolutely not. You can't take a current and add it to a B. Right? Those are different things. Just like you can't add a length to a mass. You can only multiply or divide things like that. So it would definitely be a product. What else do you think might play a factor besides I and B? Something else might play a factor. What do you think it is?
Volts.
So volts will change the amount of current, right?
Oh, right.
So volts will affect the amount of current. What do you think, Malcolm?
Is it like length of a path?
Thank you. This is not an intuitive thing. How much wire I have going through that thing there, the amount of wire that I have going through that magnetic field matters. And so one of the reasons I told you we often wrap a wire numerous times, that effectively increases the length of wire that's going through that magnetic field as well. So the equation that you'll see, it's a fairly straightforward equation. It's simple to do. It's just ILB. The sine of theta is something that people will not always understand why. I'll clarify and clean that up here in a moment, but ILB sine theta. It depends on those three things and the angle. Well, there's two of those things are vectors, correct? I and B. Theta represents the angle between them. If they are perpendicular, the angle between them would be 90, and the sine of 90 is 1. So all we're going to do in this class, I will only use force is equal to L. So first time we've seen that equation. F equals m times a is how we computed force before, mass times acceleration. Now we're going to be able to look at that as force is equal to ILB, because we're going to assume that the angle is always perpendicular, so we get the full product. Okay. I'm going to show you a few equations on that. Or a few examples. This is just quantifying that amount of force. The hard part, again, will be determining the direction. So let's take this first one up here. It's a 22-volt battery, supplies current to a resistive load. As shown, it's 5 centimeters in length. That wire passes through a magnetic field of 1.2 Tesla. It's actually pretty strong. A 1.2 Tesla magnetic field is pretty strong. The measured force on the wire is about 1.2 millinewtons. I'd like to determine the resistive load on that device. So I'm going to start with the equation F is equal to L. And I'm looking for the resistance. Now, when I go through to do this, we know some relationships between current and voltage. And that relationship is that I is equal to V over R. So I could go through and say force is equal to V over R times LV. And since I'm looking for the resistance, R would just be the voltage multiplied by L multiplied by V divided by F. Now, got to talk a little bit about units. All the things on the right need to be in the SI base unit for that quantity, so that the things on the left will be in the SI base unit for that quantity. What is the base unit for resistance? What do we use? The ohm. I want R to be in ohms. That means volts needs to be in, or the electric potential has to be in volts. L must be in what?
Meters.
B must be in Tesla. And F must be in. So this is millinewtons. That's centimeters. So if I'm going to get the right value for ohms, not milliohms or kiloohms or microohms, I want ohms. I need to have everything be the SI unit. And then we just multiply. So I take 22 volts of electric potential. I multiply that by a length of 0.050 meters. The Tesla value, 1.2 Tesla. And then I divide that by a force. What is 1.2 millinewtons in newtons? If you're going to make a mistake, it's on that stuff, right? Because you can do the algebra.
2 zeros.
Yeah, thank you. Well, it depends on whether or not you put the other zero there, right? 0.0012 newtons. Now, when you go through and do that, use your calculator for it. The equation is fairly straightforward. Pay attention to the units. The direction becomes the important thing. Okay. What is that value? 1,100? Okay. So we would say the amount of resistance there is 1,100 ohms for that circuit. Can you guys verify that that force is upward on that cable? Can you verify it? Yeah, so this is exactly, and no one's doing what he should be doing when you guys take your quiz. Seriously, when you take your quiz, you'll see, people walk by my classes from time when we get into these things that are three-dimensional quantities, and they're like, what the heck are your students doing? Because they're doing this weird stuff because they're trying to determine what's the direction of this particular thing. And it's common for people to do that. They're like, wait a minute, that has to be going, and they do that and say it's down. It's common, so you expect to do that. Okay. The bottom example is how we might measure magnetic fields using electrical current, because it's really hard to measure the strength of the magnetic field. But we can do that with this apparatus. First, I want to zoom in on it so you can see it better. I know that your copy is not very clear. You might not notice that this region here has a series of dots. Can you guys see those things on your paper? Okay, those dots are showing a magnetic field that's pointed a certain way. So the notation, when we get into three-dimensional things, which is what we have here, is we will often use for things coming out of the board or into the board, we'll use a dot or we'll use an X. Think of this the way that it was explained to me, and I always remember, is that think of that as an arrow coming out of the board. So if you saw an arrow coming out of the board, it looked like a dot, right? You'd see the arrowhead coming at you. If it were going into the board, you wouldn't see a dot, you'd see something that looks like an X. And that's because you'd be looking at like the fletching, where it looks like it's an X going into the board. So that's showing a magnetic field that's pointed that way. Now we have a current being run through this wire. Is current fairly easy to measure? Just hook an ammeter up, right? We can measure current fairly easily. This is a force sensor, and so if I wanted to measure, I can hang that thing from a force sensor. It has to be pretty delicate to be able to measure small amounts of force. But I could do that, and I could determine the strength of that magnetic field by looking at how hard that field pulls down on that portion of the wire. Can you guys confirm that the force is down on that wire? We need to practice this today. You take your fingers, you put them in the direction of I. In this case, I and this wire is flowing towards the right, correct? Correct. I would take my fingers of my right hand and I'd point them towards the right. But I have to be careful because the magnetic field is pointed outward, so I'd have to turn my hand this way so that the fingers would curl in the direction of B. And my thumb points down. The direction of force on that bottom portion of that wire is down. So it would pull down on that force sensor and we could measure that force pretty accurately. What I would like you to do is tell me what is the direction of the force on that portion of the wire. There's current flowing through that. That current is flowing up there. What's the direction of force on that portion of that wire? Once you have it, turn it to the other person that you're sitting next to. Yeah, this is what we're practicing. If I had my camera, if I had this thing going right now, I'd point this thing out here. I don't have it going, but I'd point this thing out there and I see all these people doing these weird things like that, right? Because that's what you should be doing. What's the direction? Not like that, no. What's the direction of that? So I take my fingers and I put them in the direction of I, which is up. And then I have to curl those fingers in the direction of B, which is outward. And you see it, my thumb points towards the right? Yep. That wire would be sort of bowed this way. It would bow a little bit. When I have current flowing through there, it's going to bow that way. Can you see it? Because the force acting on that thing from that magnetic field would pull it outward. What would happen to this portion? So again, folks, this is the part we have to practice. What would that portion is in a magnetic field? Which way does it go? I take my fingers and put them in the direction of I. Thank you. I put them in the direction of I. I curl them in the direction of B, and my thumb points towards the right, or towards your left. And so this portion of the wire would sort of bow this way. And that's because there's a force acting like that. Do either of those two forces contribute to the force on the sensor? No, because they're right angles to that sensor. So even though these things are bowed, you see them sort of bow a little bit, the amount of force acting could be measured with that force sensor, and from that we can calculate B. Now that we understand the direction, you guys calculate B for me. You guys can do that really quickly, right? Take a moment if you haven't done it. Jonathan's already got it done.
1.37.
Yep, just take a moment and then we'll check it.
Can we abbreviate Tesla with a capital T?
Yeah, I believe that's the symbol that we use. Is that what Google said?
No,
What did it say?
I didn't. Look it
Oh,
up.
okay. It's newer to me too. I'm being honest with you, Michael. This is newer. I studied this 30 years ago when I took classes on physics and stuff, but I haven't been able to teach it. I just never had time to get to it. So it's newer. Capital T.
Is it capital?
So again, force is equal to ILB. I'm looking for the magnitude of B, so it's just F over IL. That force is 3.48 times 10 to the negative 2 newtons. I is 0.245 amperes. And the length has to put that in meters, so 0.100 meters. And Malcolm gave me that, what was it?
1.37 T.
I got 4.2.
1.42?
Yeah.
I'm trusting that I'm going to go with the majority rules on that. That's okay?
What? I just got 4.
What are we getting?
Oh, I switched the 5 to 4.
All right, one more time. This makes for a horrible video. Sorry. What's the number? 1.42? Good. We're ready to move on. All right.
The length is on 10.
So yeah, I just got to. Are we good?
Yeah.
All right. All right, last one. I'm going to see if you guys can do number 3 completely on your own. It is a level 1 problem, which means it's typically just plug numbers into the equation. Try that one. And then we're going to look closely at that speaker setup, because that speaker setup is something that can cause problems. So go ahead and take a moment, see if you can do number 3 all on your own. I know that when I put this number together, I think I made a mistake with that number because it's a really, really big current. Yeah, I'm like, so I'm like, I'm going through this. I'm like, I made a mistake. What's the number?
2,840.
Anyone confirming?
0.9.
All right, I'm going to write it like that. Units?
Amps.
How many coulombs per second?
2,000.
2,840 coulombs per second. My household current limit, I have a breaker panel in my basement, has a 200 amp breaker on it. I mean, that's a lot of current, right? So my gosh, that would run, what, how many, 10, 12, 14 houses, right? Did I do that right?
What's your break?
It's a 200 amp breaker.
14, yeah.
About 14. I mean, that's a lot of current, right? So somewhere that might be a mistake on the numbers. All right, guys, I want to. You notice that F is equal to ILB is not too bad. I want you to practice this here with the direction. So I showed you a working speaker yesterday, correct? Okay, if you didn't watch the video there, it's sort of cool to see. I will have you guys make a speaker if we have time. If I would do that, it would be after we get through next week. It'd probably be one of the days where you're like, hey, we only have half the class here, build a speaker and so forth. You notice the thing on the left is is a permanent magnet. You have a north, south, north. So this is a special design for a magnet that has a north pole in the middle, and then you have two south poles, one on top, one on bottom. What I would like you to do is to determine the direction that the upper portion of this cone is exerted a force on due to that set of wiring. Now you notice I had to zoom in so you can see which way is that current flowing in this yellowish bar. Which way is it flowing? There's X's there, so which way is it flowing? Into the board. So you might notice that the current is flowing out of the board and then flowing into the board, and then it's wrapped numerous times this way, correct? What's the direction of force on that portion of the cone due to that magnetic field? Which way is it pointed? To the right, to the left? Is it up? Is it down? Which way? Take a moment, see if you can figure that out. So be careful. The current's going out of the board here. Or I'm sorry, the current's going into the board. Those X's mean the current. Each one of these things, it looks like I've got 1, 2, 3, 4, 5, 6 turns, right? That's showing 6 turns of wire. At that particular point, the current is flowing into the board. Down here, the current's flowing out of the board. So which way is that top portion being having a force exerted? It's to the right. If you don't see that, I'm going to show it to you. It's to the right. So I take my fingers and put them in the direction of I. Put my fingers in the direction of I. Would you guys agree my fingers are going to go into the board like this? I have to curl them in the direction of B. I see that B points up at that point. So I curl them upward. My thumb points to the right. So this portion of that cone is being pushed this way with a force. How that cone gets pushed to the right is through the magnetic field pushing on those wires, and it's pushing them towards the right. Can you guys see it? Okay, so that portion of the cone would be driven rightward. What about the bottom portion? You notice the current is flowing which way now? The current is flowing towards you, correct? I notice that the magnetic field is pointed down. What's the direction of that force? It's well, you said to the right, but you pointed that way. It is. So look, I take my fingers, I put them in the direction of you, I curl them down, and my thumb points to the right. So that cone would be being pushed that way with both top and bottom. Does that make sense? It's being pushed to the right. Now, folks, this is an alternating current. I am showing that current at one point in time. If this is current and this is time, that's alternating, which what that means is that that signal looks like so. That portion, when the current is in that portion of that wave, that cone is being driven to the right. What happens when it's driven, when it's in the other portion of that wave, when it's here? What happens?
As it back to its original position.
Well, now those things are going to be exerting a force on this one, right? So what would be happening is that force is constantly changing.
So it's oscillating.
It's oscillating. That's how we get that oscillation. You guys see it? Really today is I got to look at this thing called Faraday's law. So I want to demonstrate, this is on evidence piece number 2. So I talked about 3 forms of evidence. One of them was that electricity can create magnetism. This one is showing about how magnetism can create electricity. This law, it's called Faraday's law, is the key to understanding how motors work, how generators work, how speakers work, or anything else, how transformers work, and stuff like that. So we want to understand how magnetism can create electricity. This is about 200 years ago, roughly. Faraday looked for evidence that a magnetic field could induce, and I'm going to use the term now, inducing electrical current is generating current. And so he used this apparatus that you see on the right. It's a drawing of it, but it looks pretty similar to that. Just have a battery, a voltage source, you have a switch. He has a toroid. A toroid is just a special kind of shape that allows for magnetic fields to be sort of trapped within a body. And then you have a galvanometer. Now the galvanometer The black boxes that you guys use to measure current were essentially little galvanometers. They are very sensitive ways of measuring current. It has to do with coil wire and a magnetic field, and was able to pick that up, so it's pretty sensitive. He found no evidence that there was current being generated when the current was, that there was any current that was generated when the current flowing through that system was steady. Didn't find any evidence of that. What he did find is that when he turned the switch on or when he turned it off, he saw the needle sort of go one way or the other. And so what he theorized is that it's not a magnetic field that induces current. It's a change in magnetic field that causes current. So what he theorized is that you had to have a changing magnetic field. Instead of moving charges, we could try moving the magnetic field. It was observed that anytime that current was created whenever there was relative motion. So as long as one thing was moving relative to something else, we could get current being generated. Now I have a visual for that, and again, I can't show it really well on a recording. So if you're having to watch this thing from home, if you were gone for today for Friday's lecture, this one will not show up really well for you. But this is to demonstrate for you how we generate electricity through a magnetic field. I should say through a varying magnetic field. So again, I have a device here with a galvanometer as the centerpiece. So this portion right here is a galvanometer. That needle is connected to a little galvanometer that allows me to detect very sensitive currents, very small currents. Here I have a horseshoe magnet. Horseshoe magnet has a north side and a south side. I have some coils here. Now you notice that this coil is a lot longer than that one. There's many more turns here than that one. Would you guys agree that the length of the amount of wire that's going through the magnetic field would be bigger for this one since I have a lot of turns? Okay. Now what I'm going to do is I'm just going to take this horseshoe magnet and put it into the coil for a moment. You guys notice that when the horseshoe magnet is stationary, I don't have any current flowing. But when I pull that magnet out, and you'll notice when I pull it out, you notice that the needle moved when I pulled the magnet out. When I push the magnet back in, I notice that it moves as well. It's not magnetism that creates electricity. What is it?
Relative motion.
It's changing magnetism, right? So the coil sees a moving magnetic field. So the magnetic field is moving relative to that coil, and that movement is what's required to be able to push those charges. Now you notice that when I insert this, the needle moves in the same direction that I inserted it. When I pull it out, the needle moves in the same direction. What would happen if I take the horseshoe magnet and I switch the pole? It should do the opposite. When I push it in, the needle goes towards it. When I pull it out, the needle goes the other way. Can you guys see it? Okay. Now watch when I go slowly. When I go slowly through this, you'll notice the needle move, but not as quickly as when I go more quickly. Do you guys notice that? That the amount of current being created depends not just on the strength of the magnetic field, but it depends on how quickly that magnetic field is changing. Can you see it? The faster the change in magnetic field, the more current I can deliver. That's what Faraday developed, is a law that said that the amount of current that's being produced is related to the rate of change in the magnetic flux. And so that's the term that we want to look at. So I want to look at this here, develop this idea of Faraday's law. The induced EMF through a coil of wire is equal to the time rate of change in what's called magnetic flux. Now, flux is the term that we would use to try to describe field. The symbol that we use looks like a Greek letter phi. Subscript B for a magnetic flux is proportional to the number of lines that pass through that loop. Now, in this case here, I have a loop that has three different orientations. One is parallel to the magnetic field, one is perpendicular, and another is at an angle. You notice that if I were to think of flux as just numbers of field lines, and I were to draw it using this up here, I would see that there's 6 field lines passing through that coil. Again, I go back to the concept that the strength of the magnetic field is related to the line density that we draw for those field lines. So if I'm using that, I'd say there's 6 passing through there. How many are passing through the coil when it's perpendicular or parallel to that? And you would say 0. And the reason for that is that it's not passing through. It's just it's not passing through that coil at all. So in this case, I have no magnetic flux through that coil. This one, I have 6 of those. What Faraday discovered, though, is that doesn't matter how much magnetic flux is there. It's how quickly is that changing. So when we go through it now, Sophia, you asked about rotating. If I start to rotate that coil, I'm going to be changing how much magnetic flux is going through the center of that. The more quickly it changes, the bigger the induced voltage. The equation looks like this. EMF is equal to a negative of change in magnetic flux divided by the change in time.
Is that symbol called?
Which one? Phi.
Is it called phi?
Greek letter phi. Phi, phi, one of those things. It's a Greek letter. Yeah, phi, phi, I got it. All right, it's a Greek letter. This is saying that the EMF is proportional to the rate of change in the magnetic flux. It's not the same as the amount of magnetic flux. It's how quickly it's changing. Now, the negative there is just due to something called Lenz's law. It's not a huge deal. It just says that the current produced by an EMF moves in the direction so that its magnetic field opposes the original change that created it. So again, I'm not too concerned about the negative sign there. You can understand that as we move through this a little bit more. I wanted to look more closely at how a generator develops an EMF. So I'm going to show you a visual so you can see how that rate of change becomes the important part. So I don't think I showed this generator visual last time, and I want to take a moment to look at it now with you. Malcolm, will you grab the lights for me?
Yeah.
Okay. Now this is a very simplified view of a generator with a single loop. So again, a generator takes mechanical energy and it converts it into electrical energy. Mechanically, something is here turning that crank. Now what I'm doing there is I'm taking that crank and I'm turning a wire in a magnetic field. There is a force acting on those charges that are in that wire that can drive current. Now you notice that the current is, well, the voltage is oscillating. Can you guys see the voltage is going up and down like a sine wave? The current would be driven by that voltage, so the current would also be oscillating, correct? What I would like you to pay attention to is when is the peak voltage being induced? Where does that occur? Where in the cycle? Does it occur when it's cutting through the lines up at the very top, or does it occur when the bar is sort of parallel and moving in the direction of V? Where's the maximum occur?
Parallel.
Look more closely at it. At the very top, I'm going to pause it right at the very top for a second. So I want to pause it right there. Oh, let's try one more time. Let's pause it right there. Do you guys notice that right at that point, there's no flux going through the loop at that point, but the rate of change of flux is greatest at that point. Can you guys see it? Yes or no? Do you see it?
Yes.
What do you think I'm getting into here?
It feels like concavity and like
Okay.
rate of change increasing, decreasing.
All your advanced math classes are doing are talking about instantaneous rates of change and summative effects. So even though the flux, when that thing is straight up and down, the flux going through it is 0, the rate of change in that flux is highest at that point. It's almost like a simple harmonic oscillator. Do you guys remember when we had an a simple harmonic oscillator? At the end points, it wasn't moving, so its velocity was 0. But where was its acceleration greatest? At the end points, right? So even though it doesn't have any flux going through it, its rate of change is greatest at that point. That's where the voltage is highest. Now, as it's going through here, I'm going to continue to resume that. As I get to that point, and all of those field lines are going through that loop, it doesn't induce any voltage. Why? Because it's not about the amount of magnetic flux going through it, it's the rate of change in that. Okay. Now, a lab that I want you guys to do on Faraday's law is a mock-up of a generator to allow you to see how the rate of change is what induces that voltage. I want to do that with you on Monday.